Last time we were talking about the following concept. We started the chapter of combinatorics and we said that there are different ways in which we can answer the question, and how many ways can you pick or choose some elements out of a set with certain restrictions. These are the most basic restrictions, but of course we can use these ideas as building blocks to consider many other choices with restrictions. So the restrictions that we considered were repetitions, no repetitions, order and not order. But of course, there are other ways of choosing elements. For example, we may only care about choosing them in an increasing order, or something like that. And there may be more than one way to do that, right? If the elements are, for example, repeated, then interchanging repeated elements doesn't affect the fact that this is increasing, or let's say non-decreasing or something like that. So we define these different symbols, and you can combine these to make much more complicated ideas. And finally, we talked a little bit about sets, and this the symbol right here, the binomial coefficient, which counts the number of subsets of a given size within a set of a fixed size. And this is what we call combinations, in contrast with permutations, right? Permutations are basically just bijections from a set to itself. And there's many things that we can say about these structures. They are quite interesting. We gave a few examples. Something that we didn't fully do is we wrote this proposition, which is that there is a formula that tells you exactly how to calculate the binomial coefficient. And I gave this explanation, which is correct, but maybe you're wondering, how can we prove this in a little bit more formality? So maybe we can spend a few minutes thinking about that. And you'll see why proving things with this level of technical detail is not always that insightful, right? So the way we've, until now, proven that two sets have the same size is with a bijection. Now, for infinite sets, that is the definition. But for finite sets, this question makes sense independent of the definition, because you could prove this in some other way, for example, by counting and then looking at the numbers and seeing that they are indeed equal. And this plays into a theme that we've used a lot in the past, which is something is intuitively or obviously true for finite sets. And then we try to abstract that definition into infinite sets where addition doesn't necessarily make sense anymore, or multiplication or exponentiation and these sorts of things. Now, we're going to talk a little bit more about that, another way to define a concept on infinite sets. But before we do that, let's focus on this last proposition. How did we derive this formula? Surely the explanation I gave is sufficient for intuition or for some small examples, but how do we know that this is true in general? So if you think about it, I do need to maybe formalize this argument. Like, how do I know that these two quantities are the same, other than with all the examples that I wrote here? So last time, let's start this class. Okay, let me actually just copy this so that it's easier. Okay, so today we start the section on enumeration. Combinatorics has many different themes, but one of them is like the art of counting things that may be really difficult to count. And next week, we will probably have time to cover some really sophisticated counting techniques. These, of course, will not be covered in the problem set, because I had to shift the problem set to an earlier date. If I'm not mistaken, it should be Saturday the 10th, which is a week, slightly more than a week from now. But the problem set is shorter, and there's also a bonus question. So it's by far the shortest, and it's also quite simple problem set. In case you weren't aware, the final exam has been scheduled for the 16th. Hopefully that's correct. Can double check for you. At 7 p.m., 7 to 10 in the EX100. Please look at the announcement. That one is definitely correct, but right now I'm unable to open it for some reason. But anyway, so we have slightly more than 2 weeks, and I think it would be good if that last week where we have, I think, one more lecture, instead of trying to cover many topics, we do like a review session. And later today, I will post a study guide for you as well. I'm finishing up some paperwork related to the final exam, and once that is done, I can post the study guide for you. Okay, so sorry to interrupt that. We were talking about enumeration, and last time we wanted to prove the following fact that if we prove, we get the formula, right? Because everything has been done cleanly so far, but this last statement that I used to prove the formula may not be that clear. So there's one way that we can formalize these things, and that is just by using sets. That is the way I like to do it. There's other ways to do it. You can do this by induction or some other way. Let's do this with using sets. This is not the only way to formalize this, but in my opinion, it is the most formal way of doing this, right? Because all of these numbers are counting things. They're counting an amount. So proving this with sets is the most general way of doing this because a set can contain anything, right? It's just capturing the idea of the amount in the most abstract way possible. So consider what? So what I want to do is, this is a product that is equal to some number. So the way I want to prove this is, I want to define a set A, and I want to take the cross product with a set B, and I want to show that these two have the same size, right? And ideally, the set A has size k factorial, the set B has size n in k, and the set C has size p n in k, permutations of n in k, right? So that's what we want. The question is, how do we define all of these sets? Now, there is one quantity here that is specifically defined in terms of sets, and that is the binomial coefficient. The definition I gave is in terms of sets. So maybe that one, we don't need to think too hard about it. So maybe let me write this a bit more carefully so you know where the argument begins. So let's do proof. And in the additional exercises of the problem set, there is something that is very easy to prove using this formula, but you will gain more intuition on how to write these types of proofs if you follow the exercise, which tells you to prove that using a bijection, right? Because it's a different argument. Using everything you know about factorials and induction, that is all good and that is all well. And sometimes it is simpler because we already developed this algebraic tool. Sometimes you lose what all these symbols mean in the first place. They're supposed to represent things that are moving around, like shuffles or subsets. And it is useful to lose that intuition when you want to compute things very quickly or get some really difficult results, but it's also useful not to forget what these things mean, right? Because otherwise you could miss the point. Okay, so consider, I think I had called it the set B. So before I need to write, consider X set with n elements, right? Let k be some natural number. And I think for this to make sense, I do need to ask to k to be less than or equal to n. Otherwise, both quantities are 0, and then there's nothing to prove. But just for the sake of not having weird cases, let's just assume that this happens. Let k and B will be the set of subsets. Okay, I'm running out of letters. Let's call this something else. Okay. You know what? Let's just call it B, whatever. So this will be the collection of subsets of X of size exactly K. And by definition, as you know, we know the size of B. That's exactly what we defined n in k to be. That's the definition of that symbol, is the size of the set B, right? For any fixed set X. Of course, X could be any set because we only care about how many elements there are in X. X plays no role. The elements of X play no role. Okay, so now we need to define a set that has size k factorial and try to compute its size. So which set do you think would be useful? Which set do you think now we want maybe green. Now we want set y, let's say, such that y has size k factorial, and where this product makes sense, right? Y multiplied with b is something easy to compute, because then if I compute this, I know that this is just the size of x cross b. That is something that we proved in one of the tutorials. One of the earlier tutorials, we proved that the product has this property, right? That it opens up cardinalities, right? So this was proved in some tutorial. Right, and if we're done with this, and we know that y has size k factorial, and b has size n in k, then all we have to make sure is that this product, this set, indeed has size p and in k, because then we're done. That's the equality that we wanted to prove, and we have these sets in the middle that are helping us do this, right? So how do we do that? How do we define a bijection between these sets? So let me just go back and show you the definition so that we're all on the same page, because not everything was done with the same level of, okay, here we go. So actually, no, it was P N K. So P N K is just defined by this symbol, right? So it's good to keep in mind what it is counting. So any suggestions on what we can do next? How do we make sense of this? Any ideas? So what we're trying to do is we're trying to find a bijection between this product that I haven't defined yet. I haven't told you what y does, right? But the idea is that y is all permutations on a set of size k. What set of size k? Well, that will depend on what element we're picking on the right side, right? So maybe we can define it like this. So for every set a, every subset of size k, we consider the following set. Let's call it y sub a, set all bijections from a to a. And as we mentioned last time, y sub a has size k factorial, right? Because there are k factorial permutations from a set of size k to itself. It's just reshuffling the elements of k, right? Okay. Now, how do we combine this with the other symbol? What is this symbol here counting? This symbol right here. It is defined as some algebraic expression, but we we picked it that way because of a certain reason, right? So what is this counting? This is counting in how many ways can we pick k elements? Exactly. So someone in the chat put it. We choose k elements, but we do care about the order, right? K elements out of n. So all we have to do is the following. Let me see. So all we have to do is we take the set A and we apply, let me add one more letter just to make things a little bit clearer, hopefully. Call the bijections F. So we take the set A and we shuffle it. We apply F to it. So this is the set A but shuffled. Let me see the chat. Okay, so someone is asking why can't we prove it algebraically? So, I mean, we can prove it algebraically. The problem with this is that the size of the set B, we don't know what the size is, right? We're trying to compute the size of the set B. And for that, what I'm trying to do is take the set B and multiply its size with k factorial and prove to you that that set has size n factorial over n minus k factorial. But we have to somehow relate those two amounts because this symbol is not defined algebraically, right? So how do we prove that that is true? We could do it, like I said, by induction. Okay, okay. So I'm getting a different question in the chat. It's a direct question in case other people can see it. Is it possible to pick from infinity? Okay, so something that always makes sense is to consider the family of subsets of a given set of a given size. So for example, out of the natural numbers, you could take all the finite subsets and ask yourself how many of them there are. And you can also take all the infinite subsets or all the sets of a fixed size. I will address this in a second because I think that's an interesting question. But let's finish this argument before I do that. Okay. Okay. Let me see. Right, I have to write this in a slightly different way because otherwise it won't make sense. So let's suppose that these elements are labeled A1, A2, A3, AK. Right? So for each of those, what you do is you take the set A and you apply F to it. Right? You apply F. I had written this as a set, which is correct. The problem is that when you shuffle the set, it's the same set, right? So if you're very strict with the notation, that will unfortunately not work. But we just apply F to all the elements of A. And this set has to be for any possible permutation and for any possible A, where A is labeled the way I already labeled it, right? Okay, so the question is, what is the size of this set? And all you have to do is observe that this set, which we can call C, the set of the size of C is exactly P and K, because that's how we defined it. I mean, that's not how we define it, but that's the example that we used last time. So it's taking a set of size K. Actually, I have to write that down. A is of size K, right? So you take a set of size K, which is what I'm doing, and you consider all possible ways of choosing the order of it. But all the ways of choosing the order of it is basically applying every possible bijection to it. So you take every possible every possible function, bijection f, inside the set, and every choice of k elements inside X. That is exactly what P and K is. But here you can tell well where where the bijection is, right? Okay. So from here, using the idea from before, we can show that P and K, which is the set, is the same as first choosing such a set F, which we could write this as a product, but that's not really that useful because we already have this bijection that I defined. And the second part is the NK. And from here, therefore, if you solve for n choose k, what you get is n factorial divided by k factorial, n minus k, because this is p and k, right? So this is how you get this formula. Now, as you can probably tell, this proof isn't very enlightening, right? It's just formalizing the very intuitive idea that we already have. And in the worst case, it even confused you. So this is why I want to emphasize that these proofs are useful in the sense that you should keep in mind what these symbols mean beyond the algebra, right? Beyond just solving for some variable, canceling out the factorials. There's some deeper meaning to all of this. And if you want to look at a very similar exercise, one that you can define way more carefully than I did now with the Cartesian product, look at the additional exercise in the problem set, and you'll see why algebraically this is very easy to prove, but with a bijection you will learn something about how these products actually behave. Okay, now I think it's a good excuse now to address the question. What about the question I got in the chat? What about infinite sets? Right? And of course, we could define this for cardinal sets. You take a cardinal kappa, you take a cardinal lambda, and you could just say, so for some set X of cardinality kappa, and lambda another cardinal. I know we didn't properly define what a cardinal is, but we did define this symbol when you put a set in these vertical bars, right? In like absolute value. So you could still make sense of this quantity. You take all subsets of your set X that have size lambda for some fixed lambda. Could be finite, could be infinite. You could be comparing this with any other set. And then you take that collection and you just count how many elements it has. This makes sense. This makes perfect sense for cardinals. The question is, how does this help us, right? So for example, if you take so let aleph naught again denotes the cardinal of the natural numbers, then you could ask yourself, if you put an aleph naught here and you want to put something else down here, for example, if you put any finite amount n, what do you think this should be? Or any n natural number, including except 0, right? Because we already know that if you put 0, then the answer is 0. There's only one set with 0 elements, which is the empty set. Now, the only other cardinal that makes sense to consider is aleph naught itself. This is a reasonable question, right? And it's not trivial. It's not nonsensical. It's a very valid question. Okay, so I'm getting some answers in the chat. So indeed, for the first one, there are always infinitely many subsets of any given size, any given finite size n. But there's only countably many of them, and I will prove that to you in a second, so that this isn't just me talking into the air. But what about the second one? How many infinite subsets of the naturals are there? Should it be the same number, or would it be some other number? What do you think? What do you think this would be? And as you'll see, even though the symbol makes sense, when it comes to infinity, these things aren't obvious, right? So recall. The countable union of countable sets is countable. We proved that. And we mentioned this in the problem sets, that the collection of all finite subsets, all finite subsets of a countable set is still a countable collection, right? So this is how you get this number. So who can tell me? Maybe I don't need to write all of these details. What should this be? I'm getting another question in the chat. Does it even make sense in context of combinations? Okay, I think I understand. So the definition makes sense, but this proposition that I'm proving right here, the enumeration, of course, this only works for numbers because the factorial, there's no infinite factorial, right? We would have to specify what that means. You could count how many bijections there are from a set to itself, even when that set is infinite. But no one would probably denote that by a factorial, and you cannot write fractions with infinite cardinals, right? So we would have to redefine what it means. And this is exactly why I say that doing algebra is useful, and doing these computations algebraically is useful, but you're losing a little bit of information. And I just proved to you that part of the information that you lose is that, well, all of the things I defined in terms of sets make perfect sense when those sets are infinite, but the algebra completely breaks down, right? Like I cannot write this into a fraction. Then we have like 0 factorial. I mean, what even is aleph naught minus aleph naught, you know? In case you're curious, and this is not difficult to prove with the theory we already covered, but it is a bit not part of this chapter. In case you're curious, the answer is that this is actually bigger. It's actually way bigger. It's a bigger set. This is the continuum, right? Not difficult. It's not too difficult to see why with the theory already covered. But anyway, let's put this like a small parentheses. This we could talk more about infinite combinatorics, and it's a topic I like a lot. But I think it is a bit out of scope for this course. But infinite combinatorics is a topic that is a thing, and people do write about it, and there's many theorems about it. And we could mention some of them because some of them are interestingly related to chapters we already covered in some very unexpected ways. Okay, now let us continue. So here's something else that I want to mention: the inclusion-exclusion principle. This is also one of those things that intuitively is very easy to prove. For this principle, I don't know if there is an infinite version. I haven't really thought about it. I don't think there is. So the idea is the following. We previously saw, I'm pretty sure this was in another tutorial, or maybe even the same one, that for any two finite sets, what I'm going to write down is also true for infinite sets, but for infinite sets, it's boring because that's how we define these things, right? To disjoint finite sets. If you want to compute how many elements there are when you take the union, all you have to do is add up the sizes of each piece individually. A natural question is, what if they are not disjoint? Right? And then something that we can immediately conclude is that, well, the union cannot possibly contain more than the sum of each part. And this is because if they were disjoint, this sum would be maximized. So if they are not disjoint, in the worst case, they overlap and the union shrinks, but it couldn't possibly become bigger than the total number of elements that I already have when I add them up, right? But of course, this inequality could be strict, and it's very easy to find examples. You could take any set of size 10 and take the union with itself. Then you get another set of size 10, but when you add them up, you get, well, 20, right? So is there something better? Can we do better than this? And of course we can do better. So the first proposition that I want to tell you about is if A is a subset of B, finite sets. Let all sets be finite from now on, because all this discussion actually doesn't make sense for infinite sets in this particular case, right? Let all sets be finite from now on, unless I say otherwise. So if A is a subset of B and you want to compute what happens if you remove A from B, then I claim that this is the same as having B and subtracting the size of A. This doesn't happen if A is not a subset of B, because if A is not a subset of B, A and B could be completely unrelated. So when I remove A from B, maybe I didn't change B at all, right? And A could be a really big set. So this symbol will not even make sense if A is bigger than B, right? If A has 100 elements and B only has 2. So the symbol and the conclusion only hold or make sense if A is a subset of B. Let's prove this. So why don't you take a minute to prove this using maybe something that's already written on the board. Any ideas on how we can prove this? Okay, so let me tell you how to prove this one, and maybe you can tell me how to prove the next one, which is just as simple as this. So how do we conclude this? So here's the trick. Okay. Okay, so people in the chat are suggesting we can use the definition of the subset. Right. But how do we know this? Like how do we conclude this just by knowing that A is a subset of B? Right? I don't want to write this using a bijection, and actually I can't because this isn't the size of a set other than the one I'm proving, right? So how do you show this? Okay, so maybe this isn't that trivial after all. So who can tell me how to prove this? Give me a formal proof that B minus A has size B minus size A. Okay, okay, so I'm getting some other answers in the chat. Right. Okay, that seems like a good idea. Okay, so the suggestion in the chat says we should consider B minus A and the union. So what happens if I take B minus A and I take the union with A? It's not too difficult to see that if I remove something and then add it back, what I get is simply the original set B. Again, this doesn't happen if A is not a subset of B, because removing something that was unrelated to B and then adding it could produce something bigger, right? So I have to remove something that was in B to begin with, so that when I add it back, I get the total. Okay, so okay, another suggestion is using contradiction. The problem with that is I don't see how to use contradiction, because contradiction would be assuming that this is true, right? Assuming that these quantities are different. But you cannot, or yes. So you're saying using contradiction to prove this equality or this equality? Okay, so if we assume that these two are different quantities, what can we deduce from that? So generally, when we try to prove something by contradiction or contrapositive, we do that because by assuming that something is false, this will tell us information that we can use to derive something absurd, get a contradiction or something like that. But in this case, assuming that two things are different doesn't really tell us much. It tells us that these two numbers, when we compute them, are different. So maybe one is 5 and the other one is 6. But what can we deduce from that? We cannot take the difference between them because we don't know which one is bigger. Okay, it would mean that there's some element in the left-hand side or the right-hand side that are different. I agree with that, but the right-hand side is not a set. So that would of course make sense if these were sets that I'm comparing, but no, this number on the right is not a set. It doesn't correspond to any other natural set except the one I'm trying to prove that this holds for. So what element on the right would this work for? It is a number, so we can just reduce that to b minus a. But in the end, you cannot circumvent the fact that you do have to compute the size of b minus a. Yes, of course, I agree. We can pick a set with that size. The problem I see, I mean, that would work, but the problem I see is that what other set of that size could you find that naturally describes that number other than b minus a in the first place? This is why this is kind of a tricky proof, right? Because there's nothing intermediate. It's just pure sets. There's no other set that you could naturally use. Okay, so let's continue with this idea. We could claim there is such a C and then prove the bijection. Yes. But the thing is, I cannot come up with right now, off the top of my head, I cannot come up with a natural set that has size B minus A that would be in natural correspondence with b minus a. The first, if someone tells me there is a difference between two natural numbers, can you find a set that has that size? My first instinct would be, oh, just take a set of size b and a subset of size a and remove it, right? So the most natural set to do this on is the set itself. And finding an intermediate set, I think, could make things complicated, but it should work. It should work. Now, let's follow this other suggestion. Yes, yes, you're welcome. Okay, so you'll agree with me that if I take a subset of B, A, and remove it and then add it back, well, I get A in the first place. But there's something important about this. This union is disjoint. It is obviously disjoint because the set on the left doesn't have any elements of A, and the set on the right is A, right? So of course this is a disjoint union. So if I take the size on both sides, then given that these are disjoint sets, I can just open this up like a sum. So this is b minus a plus size of a. And notice that I'm done. Maybe I have, if I want to be very formal, I should maybe say since a is a subset of b, then b is a subset of a. So sorry. I don't know what I said. I meant since a is a subset of b, the size of a is at most the size of b. So it's hard to talk while I write at the same time. So if you take this number and you subtract this other number, whatever happens will stay in the natural numbers. So everything makes sense. This is more like a comment, not really that necessary. But if we solve for the size of b minus a, this is b minus a, and so we're done, right? Okay, so it turns out maybe this wasn't that obvious. Okay, I have another proposition for you. For any finite sets. Of course, this only makes sets for us. This only makes sense for finite sets. You cannot subtract infinite amounts. For any a, b, um, the size of a union b is the size of a plus the size of b. This happens if they're disjoint, but if they're not disjoint, maybe it's not too hard to convince yourself that all you have to do is remove the intersection because maybe you overcounted, or actually you always overcounted. Let me tell you why this is obvious, and then you can give me a proof. So this is A, and this is B. If I take A union B, I'm trying to count everything that is in either set. But if I count everything that is in B, and then I count everything that is in A, since they overlap, I am counting everything in the intersection twice. So how do I make sure that I am not overcounting? Well, just remove everything. Sorry, there's a typo here. This, of course, should be the intersection, right? You should remove everything. So intersection gets counted twice. You should remove everything that was double counted. So remove the intersection once and then you're done, right? How do you prove this formally? Let's maybe write a proof. And in the meantime, I want you to think about what happens if there's more than two sets. And as you see, things start to become a bit more complicated. So this is A, this is B, this is C. How do I count how many elements there are in total? Because the problem is now, if I count everything that is in A, and then I count everything that is in B, I overcounted the intersection. So according to the rule that I just proved, I need to eliminate that. So I have to subtract the intersection one time. But when I add a third set, I am removing the intersection of the three sets one too many times. Maybe I can make a better sketch of this. Let's use different colors. And maybe it makes a little bit more sense. Okay, so the problem is the following. I have A, and I counted A. Then in the next step, I am counting B, which is everything in blue. And I remove the intersection between A and B so that I don't double count it. For the final step, I am counting everything that is in C, and I remove the intersection between B, and I also remove the intersection, between A. And notice that there is a gap because the very center, I removed it. So in now, instead of removing it, I need to add it back. So in this case, if I want to calculate a union B, union C, it is okay if I just add the individual sizes using the rule that I haven't proved, but I just convince you this is true, which you will help me prove in a second. I need to remove the intersections, right? So AB minus A union C minus, how many do I have? B intersection C, not union, intersection. But then the very center, as you can see now, is empty. So those elements didn't get counted at all. So I have to add it back. A intersection B intersection C. And you can see where this is going, right? If I have 10,000 sets and I want to compute the union, it becomes very messy very quickly. Because if you add a fourth set, then the intersection of any three sets gets added back according to this rule. But then the intersection of all four sets is counted multiple times. So I need to remove the intersection. So I need to add up different combinations of intersections, if that makes sense. So let me know if the example with three sets was clear, because the next theorem, of course, will be generalizing this for any number of sets, any finite number of sets, right? For infinite sets, this doesn't make sense because subtraction doesn't make sense in infinite sets, unfortunately. Okay, before we do that, can we maybe together prove this statement for two sets? It's not that difficult based on things we already did. And it's almost, okay, I'm getting some answers in the chat. Let me see. Okay, so here is a suggestion, I think, for dealing with three sets. Why not calculate A union B first, and then consider union C, which is a union of two sets? Yes. Okay, that's a very good idea. Okay, so according to Yi Yang's suggestion in the chat, Why did I do it this complicated way, adding them individually? Why can I not just do the following? So if I want to compute A union B union C, I know how to do this for two sets. So why don't I just split the task into two sets, right? Because now I have two sets, and obviously it's associative, so this is still true. And you'll see what happens in a second. Okay, so according to the rule for two sets, this is the first set plus the second set minus the intersection A union B. Sorry, I'm running out of space here. Not being very organized today. And in the meantime, someone else in the chat already gave the correct suggestion for how to proving this, and I will get to it in 1 second. So this is what the rule tells us to do. Now we can apply the same rule for two sets again for A union B, right? So this is A plus B minus the intersection of A and B, right? And let's not forget the other part, minus A union B. But what is A union B intersection C? That is something that is not that easy to calculate. It still has several unions and intersections. So maybe I can expand that out. And I just use distributive laws, right? So this should just be A intersection C union A intersection B. Sorry, C. A intersection, wait, this something's weird here. B. B intersection C, right? And if I write all of this together, I have A, I have B, I have C, and then I remove A intersection B, and then I remove, actually I don't remove anything. I remove this bit right here. And this is also a union of two sets, so I once again apply the rule. So this should be A intersection C, the first set, plus the second set, which is B intersection C, minus the intersection of both sets. A intersection C intersection, there's two C's there, but of course intersecting them doesn't make any difference. And I think you can see where this is going because you get the same result we had above, right? If I remove this parentheses, all I have to do is flip the signs, right? So this becomes a minus, this becomes a plus, and that's correct. That's correct. You get the same thing. Okay. Now someone is saying, wouldn't this cause more trouble when the number of sets gets bigger and bigger? Using the normal way will make it more ordered. Is that why? Yes, exactly. So this is already cumbersome enough for three sets. If you have 100 sets, then expanding this out step by step would take way too long. Of course, we could do this inductively, because if I add a fourth set, you already have a formula for three sets. So all we have to do is include one more set and apply the formula for the first three sets. Or you could split it into 2 and 2 or something like that. That is actually the purpose of today's quiz. Not to do this for a fixed number of sets, but to do this by induction. So before we do that, let me just write this down, and then we can, you know what, instead of a break, I think it's better if we simply finish earlier today, since this principle was the last thing I wanted to explain today anyway, and it might take some time to absorb it. Okay, so how do we prove this? How do we prove the case for 2? I already told you how to prove the case for 3 assuming that the case for 2 is true. And you can see the inductive argument forming here, right? Okay, so I'm getting lots of good feedback in the chat. Okay, so how do we prove this? So the way we prove this is by using the same trick as before. We add and remove the union, right? So if you take A union B, you can just write this as take everything in A that is not in B, then take everything in B that is not in A. This is the symmetric difference which we defined sometime in the past. And then take everything that is in both. These are clearly the same set. Something is in A union B if it's either only in A or only in B or in both. And these unions are all disjoint. because this one has nothing of B, but this one, is a subset of B, and this one has something of both. So all of these are pairwise disjoint, meaning if I take the absolute value, not absolute value, but the cardinality, all I have to do is split this. So this is the set of A minus B. Okay. Yeah, let's just write it like this. We can use the thing we had above, right? Where is it? The proposition you can see at the top of the screen that says that the size of B minus A is B minus A. Now, we have to be a bit careful here because A and B are not subsets of each other. So instead of writing it like this, I just have to include the intersection. Why? Because the intersection is in fact contained in A, right? If there's anything that you want me to fill in here, let me know. There's nothing weird going on, right? So this is just B minus, I should write A, but of course I only care about the part that is also inside B. And for the last bit, this is just A intersection B, and I have no way of simplifying that further, right? Now, does that even make sense? Okay, let's see. Okay, so in the chat, people are asking, A minus B, should we write it instead of A minus A intersects B to make sure it's a subset? Yes. So A minus B makes sense as a set, but to use the proposition to make sure that it is in fact a subset, we do need to write it with the intersection. Yes, that would be the intermediate step that I skipped. You know what? Let's just write it down because otherwise it might seem like I'm skipping too many details. Okay, let me be a little bit more organized here. Okay, so what is A minus B? To remove the set B from A, I only need to remove everything that is already in A, because otherwise I'm not removing anything, right? There's no need to remove that. So let's write it like this. Same with B minus A. Removing something is the same as removing the intersection, right? But the definition of remove doesn't require them to be subsets of each other. So this is just to add some clarity here. These are the same, right? And then I have this right here. And then I have this. Okay. So this is by the first proposition. Okay, so all I'm doing is splitting this into a sum, and then the first one is just that. Okay, so if we cancel out whatever terms repeat, this is just A plus B minus A intersection B, right? I'm done. Questions? Any questions, or does this make sense? I have minus minus plus, right? So it's just minus. This is the end of the proof. Okay, and as you can see, it becomes rather cumbersome for 3 sets. But what if you add more? So let me write down the theorem. It makes sense. Okay, thank you. Let me see. So the main theorem, which is the inclusion-exclusion principle, which is very useful, and there's a lot of consequences of it. The theorem is that the size of A union, maybe I should label them 1, 2, all the way to AK, all finite sets, of course. If they're not finite, then this will not make sense. This is what? This is what? Let's write this with N. So this should just be, first you add up all the individual sizes of sets from the first one to the last one. And then you have to remove all the pairwise intersections of them. So AI intersect with AJ, right? With I, you only have to do it once. So let's say I less than J, both less than N. And then you alternate the signs, minus, and the correct way of doing this is let me introduce the variable r, where r is whatever size follows, right? So you first do the pairs, then you do all the subsets of size 3, then all the subsets of size 4, and so on. So here we're doing all the subsets of size r. And by subsets, I mean you take all the subsets of this family of AIs, and you either add or remove, alternating, the intersection of all of these. Now, this might seem not that useful to generalize it to this extreme point, but keep in mind, you can use this, for example, for one of the problems in the problem set. The hardest one, which is, I think, counting the surjective functions, requires this result. And if I recall correctly, it requires it in this full generality. And you do this all the way up to size n minus 1. Of course, the ones with size n is just the intersection of all of them. And yeah, this is just the intersection of all of them. And we have no way of knowing what that size is going to be, so let's just take the intersection like this. So this is the theorem, and it might seem very cumbersome, but it's not more difficult than the idea we already set up here. You basically need to take the union, you add up the individual ones, and then you remove the pairs, and then you add the triples, and then you remove the sets of size 4, and then you remove the sets of size, you add back the 5, and you alternate, right? So we can prove this directly, and I will do so in a second. But the exercise, which is the more algebraic approach, which is not necessarily the one I find best, but it's similar to what we already did up here, and this is today's quiz, is prove this by induction. Now, how would you not prove this by induction? You would have to do some intuitive argument where you count the sizes of the sets on both sides and see that they're equal, and convince yourself that this makes sense for any number of sets. But I think that the example I gave with 3 sets covers enough intuition because, yeah, I mean, there's no point in being overly confusing. So let's just leave it here. Maybe let me add one more way of writing this, because there's a way to simplify the notation, right? So here's a better way of writing it. And you can choose to prove it either way of writing this. And next class, which is on Monday, we will cover some applications of this, some more examples of the pigeonhole principle, and maybe on Thursday I will cover one more theme. That way we have 3 subjects, only 2 of which get evaluated as part of the combinatorics chapter. And I think that's more than enough. This will be a shorter chapter compared to the previous ones. Oh wait, you're right. Monday is a holiday. Well then, okay. In that case, it will all have to be on Thursday. Yes, thank you. Thank you for letting me know. There is no class on Monday. Okay, that's okay. I will then have to schedule additional office hours, but I will let you know, probably on Tuesday. Okay, here's a better way of writing this. Let me see. Okay, so for each okay, how do I write this? Let me think about this. For each t, every time you take a subset of the indices, right? They go from 1 through n. Write n of t for the size of the intersection of whatever indices you grabbed, right? Then the same theorem, says that the size of the union, oh, bad time for this not to work. Okay, I'm getting questions about the final. So the difficulty of the final will be, in my opinion, will be slightly more difficult than the easiest exercises that you covered in the problem sets. but probably a little easier than the harder ones. And I'm trying not to include any long exercises. So the focus of the final should not be necessarily to solve a very difficult question quickly, but rather to write a detailed and complete proof with adequate language. That's the most important aspect, I think, because it is an introduction to proofs, right? This course is supposed to be an introduction to proofs. So I will give you similar exercises for you to know what I mean by this. Yes, like I said, I will post a study guide later today so that you know more or less what to expect. And I also don't believe in having long finals, but there's some paperwork I need to do today. After that, I will post this. Okay, so my pen decided to act up again in the worst possible time. Okay, so I think can I do something very tricky here? Probably not. Probably not work at all. Okay, kind of. Okay, so the union of all of these sets should be equal to something, and that something, um, it's kind of unfortunate. That something is you take the sum out of all possible subsets of the indices, which is 1, 2, dot, dot, dot. Can I compile this? And then you take minus 1 to the t, the size of t, okay, plus 1, so that they alternate, and then n of t. And this something doesn't make sense. There we go. Okay, so give me 1 second. Since my pen decided to stop working, maybe there's a way for me to compile this. Let's see if I can find it online. Okay, how about overleaf? Okay, in the meantime, are there any questions about anything I've done? You can start thinking about the quiz, which is proving this by induction. And like I said, it's no more difficult than the thing we already did with the example of 3, because for the example of 3, we used the formula for 2 multiple times. Okay, nice. Okay, let me just paste this so that the notes are somewhat completed. There we go. Okay, so that's a much shorter, nicer way of writing this. It doesn't require all of these dots and stuff in the middle. It's the same idea, right? You're increasing the size of NT because you're adding more and more sets to the intersection and taking all possible combinations, all pairs, all triples, all quadruplets, whatever you call it, quintuplets, and so on, until you're done. And in the end, you have to deal with the intersection of all sets. You either add it or you remove it depending on the parity of this. Okay, I will stop the recording now, and I will stay here